This is lesson 6.07, moles and chemical equations. Chemists use moles and equations to calculate the amount of reactants they need or the amount of products they produce. How much of any reactant must a chemical use in a reaction? How much product will the reaction make? Chemists use the information in chemical equations to answer such questions. You will use the information you have learned about converting various amounts of chemicals to moles, along with chemical equations to predict not what, but how much reactant you will use or how much product you make. So amount of chemicals found by using conversion factors or conversion fractions. Amount of chemicals found by relating mole volume relationships, chemical equations, and molar mass. Again, molar mass, the mass of 1 mole of the substance. Goals for this lesson. Demonstrate understanding of the law of multiple proportions in chemical formulas. Remember, law of multiple proportions talked about the fact that you can't use half of an atom and you always have the whole number ratios. And the second goal, predict yields or how much of products of a chemical reaction will be made when given molar quantities of reactants or products. So if you're given 5 moles of something, how much will it make? Again, there's the student guide for you. Chemists need to figure out quantities of reactants and products. How much nitrogen and hydrogen must be combined to make 10,000 liters of ammonia for fertilizer? How much nitrogen yes, sometimes it's hard to say, tetroxide will be needed to combine with 1,000 kilograms of dimethyl hydrazine rocket fuel for a rocket booster. These are the kinds of questions chemists ask in real-life situations. Such questions are answered by using principles of stoichiometry. Just a hint, when you are pronouncing the chemicals, please don't just read over them. Try and break it up. So I have di meaning 2, methyl, and then hydra, like hydrogen, and then zine. And this one, tetra means 4, and then oxide, obviously oxygen. Look at the generalized equation. It says that A moles of reactants X combines with B moles of reactant Y to make C moles of product M and D moles of product N. In other words, okay, you have your reactants, which are the lowercase letters. The X and Y go together, and it's probably a double displacement reaction and makes the products, and you can have different amounts. Remember, we counted how many molecules were on each side of the equation before? That's what this is talking about. Any balanced chemical equation relates the number of moles of product to the number of moles of reactants. A chemist uses a chemical equation and stoichiometric calculations to figure out amounts of reactants and products. Balanced equations are the key to determining the amounts of reactants and products. Balanced equations have the same numbers of each atom on both sides of the equation. So if there's 5 hydrogens on the left, there's 5 hydrogens on the right. Here are some tips for balancing an equation. Do not touch the subscripts. Balance by adjusting the coefficients of the formula. Remember, the coefficients are the large numbers to the left of the entire chemical. You cannot throw a coefficient in the middle. It's got to go to the left. To the left, to the left. All your coefficients go to the left. That's right. Now you'll remember. Balance the different atoms one at a time. Balance atoms that appear only once on each side. Balance polyatomic ions as a unit. In many cases, balance hydrogen and oxygen atoms after others have been balanced, because those just tend to magically work out. And make sure the coefficients are in the simplest ratios. All right, so balancing some equations. So you have your story problem here. In a rocket fuel, liquid hydrazine, which is N2H4, and liquid dinitrogen tetroxide, N2O4, combine to form gaseous nitrogen, N2, and water vapor. All right, so start by writing down your equation on a piece of paper, and then you want to go through and list all the elements. It really doesn't matter what order you list them in. However, You want to list them in the same order on both sides because that will make it easier for you in the long run. And again, you should be doing this on paper. Try it by yourself first and hit the pause button. And when you're done, check the answer to fine. All right, how many nitrogens are on the left-hand side? I have 2 plus 2 gives me a total of 4. How many hydrogens are on the left? 4. And how many oxygens? 4. Right-hand side or product side, how many nitrogens? 2. How many hydrogens? 2. How many oxygens? 1. All right. So, like I said, you almost always save oxygen and hydrogen for last. And the only exception is when you have an element that's by itself, like you have this one right here. That's usually the best to save for the absolute last because it's easy because whatever coefficient you put in front of it, it only affects that one element. It only affects the nitrogen. So this is kind of a rare case where we're actually going to do the hydrogen and oxygen first. So we have 4 hydrogen on the left. We want a total of 4 on the right. And we also want a total of 4 oxygens on the right-hand side. All right, so we have a problem because we have to multiply. And so our oxygen tells us that we want to multiply by 4. Our hydrogen tells us we want to multiply by 2. Which one are we going to have to go with? We're going to have to go with the 4, even though that gives us too many hydrogens. That's okay because we can take care of that later. So we'll have 8 hydrogens and 4 oxygens. Where am I going to add that? I'm going to add it to the front. So I'm going to put a 4 right there. And then my 4 distributes. So that's how I have 8 hydrogens. 4 times 2. 4 times 1 gives me 4 oxygens. All right. So if I look at my left-hand side, what do I need more of? I need more hydrogens. Okay, so let's balance the hydrogens. I need a total of 8 hydrogens. So what coefficient am I going to have to use? Since we multiply, we need a 2. And where am I going to put that 2? Put it right in front of the entire compound. It has to go to the left, to the left. Coefficients always go to the left. All right, I just ruined that song for you, didn't I? Haha. All right, so now we distribute. And how many nitrogens do I have? 2 times 2 is 4, plus 2 gives me how many nitrogens? 6. And then I distribute 2 times 4. I have my 8 hydrogens. All right, let's balance our nitrogens. I want a total of 6. So what do I multiply by? 3. So what do I put in front of my nitrogen? A 3. And that is my final balanced answer. So we reviewed balancing because balancing is so important when we're talking about the stoichiometry because that helps us with our mole ratio. Mole ratios relate products to reactants. Dalton's law of multiple proportions states that when elements combine, they do so in the ratio of small whole numbers. This law explains why the subscripts and coefficients of chemical equations are always in whole numbers. The coefficients represent the number of moles of substances. Okay, that is huge. We're going to add that to our note. And from the previous slide, we're also going to add our top sentence here. So we are going to add balanced equations are the key to determining the amounts of reactants and products, and the coefficients of a balanced equation represent the number of moles of substances. That is huge. In fact, you should probably underline or bold it, okay? Because that's going to help you with all your stoichiometric problems. All right, so that was our big sentence. The coefficients represent the number of moles of substances. The ratio of the moles of any two substances is called the mole ratio. The most useful mole ratios are the ratios of the moles of any product to the moles of any reactant. Product-reactant mole ratios help you relate the left side of the equation to the right side. And we'll look at the examples. Also on our notes, before we get too far and I forget, I added the keywords and pronunciation from the study guide. Limiting reagent, the reactant that is completely used up in a chemical reaction and thus governs how much product can be made. So in other words, which reactant runs out first, okay? And the mole ratio, the mathematical ratio used as a conversion factor when solving problems in stoichiometry. Or, let's add our definition that helps us out a little bit more than that one, the ratio of the moles of any two substances. All right, let's go ahead and look at some problems. Now, those of you that watched the Unit 6 lab recording, you may remember that we talked about ratios, and that's what we're doing here. So, it says mole ratios start with a balanced chemical equation and compare the moles of various substances. This should be read as follows. 3 moles of N2 result from 2 moles of N2H4. Or you could also say 2 moles of N2H4 produce 3 moles of N2. All right, so if I have 2 moles of N2H4, how many moles of water will result? Well, it would be 4. My ratio is 2 to 4. I could also change it. I could say, what if I only had 1 mole of this? What if I only had 1 mole of N2H4? Now how much water do I have? Well, my ratio is 2 to 4. So if I only have 1 mole over here, that's half as much, I'd only have 2 moles of water. All right, so it's showing you that you can set up any combination of these. Any combination of, if I have 2 moles of this, 1 mole of that. If I have 1 mole of this, I will get 3 moles of that. So you can set up any ratio. If I just ask for the ratio of reactants, that's 2 of the N2H4 needs to react with 1 mole of N2O4. And if I ask you for the products, that says that I will get 3 moles of N2 and I'll get how many moles of water? 4 moles of water. And so I just added the first example here in our notes just so that you would have it. You can handwrite it out, you can snip it. If you don't have the program Snippet, it's literally like this, snip it. Google it, find it, it's so helpful. It's a real easy way to take just tiny screenshots, and I use that a lot. All right. How do you use mole ratios? For a given chemical reaction, if you know the number of moles of any reactant and the proper mole ratio, use simple algebra to get the product. Return to the example of the rocket fuel. Suppose you're giving 3 moles of N2O4. How many moles of water will result if you combine 6 moles of N2H4 with 3 moles of N2O4? All right, so write it down to start with, and then let's look at what they give us. They say I have 3 moles of N2O4. So they're saying I have 3 moles of N2O4. And let's put that in the right spot. I have 3 moles of N2O4 and 6 moles of N2H4. So 6 here. First, I want to check. They said that I have 6 to 3. Is that the same as 2 over 1? And 2 over 1 I got from our original setup. And yes, they are equal, so I can legally, according to the math rules, use these numbers. So like all our problems, I start with what we know. You can pick either one, it doesn't matter. So 3 moles of N2O4. What has to go on the bottom of my next fraction? It has to be moles, but specifically moles of N2O4, because that whole thing has to cancel. And what am I converting to? I'm converting to moles of water. So look at my original equation. I have 2 moles, 1 mole, 3, 4. Use the correct one. I'm looking for moles N2O4, which is 1, and water, which is 4. Put it in my calculator and I get an answer of 12 moles of water. Hit pause, look it over, make sure it